so we were, a fair way into permutations. Just let's kind of review permutations for just a second. Let's say we have 3 objects. We have, let's do cat, dog, ferret. And if you select cat first, so, we're just going to take 3 and permute all 3 of them. And we can take a look at what this looks like. So here's the first selection. Our second selection is going to be, oh, thank you. I am not screen sharing, and I should be. Okay. So we've got C, D, and F, cat, dog, ferret, and we have our first selection, which can be any one of those, and our second selection we can build from the first selection, right? If we select cat first, we'll either select dog or ferret. If we select dog first, we're either going to select cat or ferret. If we select ferret first, we're either going to select cat or dog. And then there's only one thing left for the third selection. So cat, dog, ferret, cat, ferret, dog, dog, cat, ferret, dog, ferret, cat, ferret, cat, dog, and ferret, dog, cat. And something to notice is that, so we've only got, we've got 6, right? 3 times 2 times 1, 6 arrangements, 6 permutations in 3 permute 3. If we do 3 permute 2, we can, work this out. This is going to be 3 times 2 times 1 over n minus k, right? So here's n minus k, 3 minus 2 factorial, which is going to be, 1 factorial. Turns out 3 permute 2 is going to have 6 as well. And we can see that. So where the 6 here, if we just get rid of this third, well, we can see here are our 6 permutations, right? So CD, CF, DC, DF, FC, and FD. So I think that's kind of an interesting thing about it. At any rate, let's go back to this. Let me center that. And let's just look at the permutations formula again really quick. So n permute k, where n is the number of items that we're selecting from, k is the number of items that we're arranging from n, and this is just n factorial over n minus k factorial. Okay. Essentially, this n minus k right here is, it represents the items that we will not be arranging, right? So we're reducing them out of the space. We're dividing them out. Okay. So the functions that we wrote, I'll go ahead and paste these again into the Slack because we will need them. So we have factorial up here. We've got 2 different versions of permutations. And this other version of permutations is just somewhat more optimal than just writing the formula as it is. So let's think about, let's build some more intuition here. This is intuition that we've already kind of built from doing this by hand, where we counted in a base system, right? Remember this? We counted, and then we reduced out anything that had duplicates in it, any outcome that had duplicate elements, and that was our factorial. And what I just showed you showed how we can, say, reduce a little bit further to our permutations from our, sort of like maximal arrangements that factorial gives us. If we want to do this in code, let's do this with a base 5 system. And this is going to be reminiscent of the counting that we've already done. Okay, so let's make a base 5 system. And this will be, we'll call this base 5. And I'd like to use symbols that are not numbers for this, in part because, I tend to like to do that because I want to break this idea of counting as being directly related to the numbers that we're familiar with. I want to use different symbols in order to kind of change this around. So let's think about this in terms of occupations. So very generally, let's just do scientists. We'll keep these small. Lawyer, I don't know, medical doctor. Think about that, and let's say, I don't know, astronauts, right? That's how it's spelled. Okay, and let's say firefighter. And we're going to use these as our symbols in this. So we'll just arrange all of them, but we're going to take this from a reductive approach, and I'm going to give you also an indicator of how we could get the permutations even from the we can do 5 permute 5, but we could also do 5 permute 3 from this if we need to. So let's do let's call this counting, and this is going to be my collector for the different arrangements that we can produce. So this is going to be reductive. I'm going to say for I don't know, person 1 in base 5, and we can just do 5 nested loops to count, right? This is our sort of pure counting. So we start at scientist, 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 and we go up to firefighter, 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 firefighter. That's a really hard word to say over and over. And we can just say counting, dot append, and it's going to be a list where we say P1, P2, P3, P4, P5. Okay. All right. So if we want to take a look at this, at what this looks like, we can say for person in counting, let's just print that list and see what it looks like. Okay. And we have counted, right? This is so what we want to glean out of this is things that are permutations, all right? What's a permutation? It's going to be any of these lists that doesn't have duplicates, right? So firefighter, astronaut, scientist, doctor, astronaut is not a permutation because we've repeated astronaut. So we need to trim that out. How are we going to go about doing that? It'll be pretty easy, actually. Let's call this perms, and we'll say for each person in that counting list, let's decide by default we think it's going to be a permutation, and then we'll qualify that belief. We'll say for I'll do it like this. I'll do p number, and then I'll say for each person in P number, right? So P num is the list of 5. P here is each item in that list of 5. We can say if P num dot count of P is greater than 1. In other words, if there's a duplicate. If there's a duplicate, we set permutation to false, and we don't need to check anymore. We know it's not a permutation, so we can give up at that point. And then we just need to check if perm is true. If perm is true, then we can say permutations.append. We can append that P num. Okay. So I'm going to say for P num in our permutations, maybe I'll make this more consistent. Let's just print that person number. Okay. And here we get this big list of stuff. These are permutations. We don't have any one of these lists where we repeat any of the elements. Okay? So let's look at this a little closer, because, and I alluded to this yesterday, I'm going to implement an algorithm, and I don't expect you to be able to do this at this point, but I'm going to implement the Heaps algorithm for permutations, where instead of doing this brute force reductive approach where we build all the counts and then cut things out, we're going to be swapping things around. Okay, and I want to show you, I want to give you some intuition for that. Okay, so firefighter here moves to the left, moves to the right, moves to the left, moves to the left again, moves down, and then goes back to the beginning. Moves to the left, moves to the right, moves to the left, moves to the left, goes down, back to the beginning. That's a predictable pattern right there. Okay? That pattern emerges because of this specific reductive approach. And if you think about it, it takes a lot less work if you know where to move it, if you can figure out a systematized way to move it. So that's one pattern that's in here. There's also going to be a pattern for doctor that should not be too similar. So here we're moving down, move to the right. Be easier to show this in a different color, wouldn't it? Do green instead. And I'm really just showing this. We're not going to be implementing this pattern, but I want to show that there is something sort of, there is something emergent here. And if we can capture this in some way, then we can implement an algorithm that would do this. And so that's a challenge if that I'll just dangle out there if anybody feels like they want to take it on. With this reductive approach, can you determine a swapping algorithm that you could use to get you permutations? I'm going to use a slightly different algorithm called Heaps when I do this, but Heaps is not the only permutations algorithm. At any rate, an algorithm that relies on swapping is not going to throw away information the way that we're doing here, right? So we're constructing all of this with all these nested loops, and then we're throwing away a very large amount of that information that we've generated. It would be nicer if we could just take these items and swap them around. So I'm really just saying this to give some basis for the next thing that I'm going to show. So let me go ahead and I'll drop this in the Slack as something to play around with. And I'm going to kind of introduce Heaps Algorithm. And again, just to be very clear, you do not need to know Heaps Algorithm. You do not need to be able to implement Heaps Algorithm at this point. But I want to give you sort of a look into this world. So Heaps Algorithm is just an algorithm to generate permutations. And it will generate all permutations of n objects, and we can write it in such a way to get us a different value of k. So if we've got n and k don't have to be the same number. We don't need to arrange everything. We can just arrange some subset. We can arrange k of the n items if we want to. So here is a swapping pattern that is used if this will load. Not sure what's going on there. Oh, there we go. Okay. So notice here we're looking at this on the left, although you can imagine we could flip this over. And we swap the first two, and then, so we can follow the path of B. And the path of B is going to take a consistent sort of form, okay? And notice we've got this run. Every one of these letters is going to have this sort of run. So 1, 2, 3, 4, 5, 6 in this case. And let's see if we can find. So here's a run of A. There's a run of D. And by the time you do this, if you run through all these swaps, then what you're going to ultimately see, and I want you to notice just that there is a pattern here. What you're going to get out of this is all the permutations. So let me show you some pseudocode. This is not very readable. Okay, and this is what I'm going to implement right here. So here we've got, we've got this thing that looks like a function header, but this is not runnable code. This is sort of algorithmic language from which I'm going to implement something. In the DSI, there will be times where you're given something like, here's some algorithmic language for this, machine learning algorithm. Implement this in Python. And that's what you'll do. But we can see that there are some things that are kind of familiar, right? We've got this thing that looks like a for loop. It's at least using the word for, and that's definitely what that is. We've got this thing that says there's an array of integers. Turns out we're going to use a list to perform this. We've got a while loop, right? We've got all these things that we're familiar with, and we've got if and else statements, right? This, I think most people in this class, if you were to take this and tinker with it, for a while, for long enough, I think you'd probably end up with a working version of Heaps Algorithm. So I'm just going to code through this pretty fast. I'll talk through it somewhat. I'll be a little bit hand-wavy as I go, but I just want to demonstrate this to give you a sense of the level of coding, that you're aiming for. All right. So, we're going to be swapping elements in our list. So I'm going to write a separate swap function. We pass in a list, and we give it two indices that we wish to swap. So index 1 and index 2, right? And from that, I'm going to say, well, I'm actually going to make a copy of the list to not modify it. And I'm going to say, I'm going to use this sort of classic I'm going to make a temp variable, and I'm going to get the item at index 2. And then I'm going to replace the thing at index 2 with the thing that is at index 1. Okay? Right? So why am I using a temp variable here? I'm using it because I'm going to overwrite the element at index 2. And then I can take the element at index 1 and overwrite it with temp. So you could write this in denser Python, but I just want to show you, this is a simple way to swap things around in a list, right? This is a simple swap function, and it should work. So at that point, we'll return the list. So let's test this. Let's make a test list, and we'll do, I don't know, we'll just do A, B, C, and D. And let's pass in this test list, and we'll pass in, let's swap index 0 with index 2. So we should see the A and the C swapped when this is run. And it is CBAD, right? Pretty straightforward, I think. If I did 1 and 2, we'd get ACBD. And we do. So that's our starting point. I'll go ahead and put that in the Slack. And now we'll get into something that's a little bit headier. And this is going to be Heaps Algorithm. And I'm writing a form of heaps that is not recursive. Okay. Now, what do I mean by recursion? By recursive, this function is not going to call itself. And you're going to find this out in the world, that there are functions that call themselves, and there are functions that do not call themselves. In general, unless there's a kind of elegant way that a function can call itself and it's not ambiguous what it's doing, a light suggestion, maybe opt for the non-recursive form of the algorithm. Although sometimes it's a little bit harder to write a non-recursive form, to be honest. Okay, so we're going to pass in a list, right? And this list is going to be a single arrangement of all of our elements. And then we're going to select k of them, all right? I'm going to make a copy of that list, as I do. And that's just so we're not modifying the thing that we pass in. Or, we're preventing that possibility. So I am going to make something called C. And this is coming straight from that algorithm. C here is going to be a thing that holds kind of a record of the operations that we're performing. And notice I'm starting at, I'm going to make a list that is the length of our number of elements, and I'm going to set all the values in that list to 0. And this is going to be like, it's going to be a bunch of pointers for indices, okay? And I'm going to say that this holds the stack state. So essentially, this is just a kind of record keeper. It's a little real-time record keeper as this thing goes. So I'm also going to collect our permutations. And I'm going to start off with the first permutation we know, which is going to be the list copy up to the kth element. So k, we're using that to just slice, if there's 5 items, this is going to include all 5 of them, if k is 5. If there's 5 items and we're only selecting, and we set k to 3, we only want to arrange 3 of them, then this will only collect the first 3. But I'm putting those in the list into permutations. I'm just getting the first one out first. And we're going to use perms here to collect our permutations. Okay, so here's where it gets a little wild. This is our stack state. This is our state, the thing that we're using to keep a record. And here's the pointer that we're going to use. So this is going to acts like a pointer to C. Okay. And I'm going to use the infamous while loop. You probably heard some people talk smack about the while loop. In Python, I think there's good reason for that. Also, this is a problem that lends itself to a while loop. We don't know exactly how many times we're going to do, or the algorithm offhand doesn't know exactly how many times it's going to have to do this. So we're just going to use a while loop. Okay. So I've got a couple conditions here that I'm going to set. If C sub I, right? So we're starting with I at 0. So if C sub 0 is less than I, okay? Then we are going to do some things. We're going to check if it's the even position, and if it is, we are going to make a swap between the 0th position and the ith position, and then otherwise we're going to make a swap between the value that's stored at C sub I and the ith position. So that's actually the heavy lifting right there. It's a very elegant little thing, an elegant little move that we're making. And we're going to start collecting our permutations. We're first going to check to make sure that a given permutation that we've determined is not already in our collection of permutations, all right? And if it's not, then we're going to append it. And there are a bunch of little utility moments here. We're going to increment our counters. So C sub I, where we're counting, is going to be incremented by 1 on each turn of this loop. And we also reset the value of I once we get down to this point. And that's in case C sub I is less than I. Otherwise, we're going to reset the state of we're going to reset our counter state, okay, for C sub I. And we're going to set that to 0. And then we increment I. So this may seem magical in some way. And I definitely encourage you to use, let's say, input statements. We can check the arrangements of our list copy, right? This is something we can do. So maybe maybe I'll demonstrate that a little bit. But first let me run this. Let me make sure this is doing what we expect it to do, and let's use our same base 5 here. So this is called, what is this called? Heaps non-recursive. And let's pass in base 5. And let's look at 5 of them. And let's get these out into, I'll just call this heaps. And so I'll say for outcome, or I'll say for perm in heaps. Let's print that permutation. Okay. So that was very quick. You may not realize how quick that was in comparison. If we had a bunch more of these, a bunch more elements, with our nested loop approach, the computation of that time increases exponentially. However, here, we're just swapping. We may be throwing away a couple operations here and there when we reproduce the same permutation, but we're just performing swaps. And at the end of this, it's not linear. It's going to be more than just than this in terms of the number of items. It's going to grow a little bit, but it's going to maintain a certain optimal performance, and that's really what I want to. I just want to say that. So, if we want to watch how this changes, I could throw an input in here, okay? And I think this is a great way to utilize input. I'm going to put in input of list copy, okay? What input is going to do, it's going to wait for you to hit return, and it's also going to print whatever's in here. And if you use input in this way, it can get you a look into your function, all right? So here's the first state of our permutations, and then we're going to swap. Actually, we're going to go to our second. This is our second loop, okay? We haven't swapped anything yet. On our third loop, we do swap something, and notice we're swapping scientist and lawyer. And then we don't swap on the fourth, and we don't swap on the fifth, right? Now we do swap on the sixth. So what you might be seeing here is that we are actually throwing away some operations. And that's fine. We have a more optimal algorithm, but we are still looping more times than we need to, than if we had a more determined pattern for the swaps. So I'm gonna stop that there. I think this is one of those algorithms that it's just really cool, and I think it's a good one to study after your technical interview. I don't want to suggest that you should study this before your technical interview, but you will be writing things like this at some point. You're going to be implementing algorithms that are at times at this level of complexity. Okay. So that's heaps, and we'll leave permutations there. The things that I want you to take away, right, from permutations. Just zoomed in. Do that. The kind of thing I want you to take away from permutations. There's a couple things, and I'm just going to reiterate these. I think I mentioned these before. 5 permute 5 just equals 5 factorial, okay? Right? 5 permute 5 equals 5 factorial. We can demonstrate that. That's one thing I want you to take away. The other thing I want you to take away is that order matters, right? Why do we say order matters? Because it is the arrangement of these items that matters. That's what we're considering in terms of permutations. And the reason I'm saying that is that there is another form of counting beyond permutations, a further reduction from permutations, where order does not matter, okay? And we call that combinations. It's kind of unfortunate that we call combination locks. We should actually call them permutation locks, because they were combination locks. It wouldn't matter the order that you put the numbers in, right? So we unfortunately have not the best association with this word in terms of what it means for us in probability, in counting and probability. When we're talking about combinations, first thing to think about, this is going to be a further reduction of the permutation space. Okay? So what does that mean? It means we're going to throw something onto the denominator. And that's going to mean we're going to have less combinations when in consideration than for a number of items than we would if we're considering permutations. So let's think about a cardinal example of this. Let's think about a cardinal example of combinations. And I think this is like maybe the classic one, and I think it's really helpful. How many different five card hands can you have in poker? Right? You've got a 52 card deck. How many 5-card hands can you have? Offhand, a lot. I'll just say that. Offhand, there's a lot. But the point here is that, okay, you know, I don't know, one of diamonds. Let's say you've got like, I don't know, king of clubs. Oh my gosh, I'm not gonna. That's basically a club or a piece of broccoli. You've got ace of spades, right? And let's just do a couple more really quick. Like, let's say you also have a 2 of diamonds or 2 of triangles apparently, but say that's a diamond, and let's say a 9 of diamonds as well. Okay. It doesn't matter what order these are in your hand, right? It doesn't matter. It just matters that this is a selection, right? You've got 5 of them, and that's what we care about. We just care about that. So something to notice first, if you have 52 and you're wondering how many combinations there are of 52, right? You have a 52 card. You have a 52 hand. Like, you have 52 cards in your hand. How many different ways can you have 52? Not permutations, not orderings, but how many different ways can you have those same 52 cards in your hand? You can only actually have one, right? So when we say 52, how many combinations of 52 are there from 52? There's only one. And I think that's an interesting facet of this, right? If you only have these 5 objects, how many, there's only one way that you can have those 5 objects if order doesn't matter. You just have them, right? So try to tie this idea together. Combinations to a 5 card hands. How many 5 card hands are there in a 52 card deck? We'll use that as as a kind of basis to start thinking about this. So just like permutations, there is a factorial based formula, and this is the way I'm going to write this. The way we read this is n choose. That's how we say that. N choose k. You'll often see this n choose r. Same thing. I think we tend to use k more in this space, but a lot in most of math they'll use r, and it does not matter. It means the same thing. So n choose k is going to be. It's going to be. Notice it is the same formula as permutations, except you reduce again. So in some sense, this is like, what are you excluding, right? You're excluding n minus k of these in the final working of this. You're excluding n minus k. You're also excluding all the arrangements, all the different arrangements of k, right? So that's kind of what that represents. So those are the different permutations of the same k items. So there's a, the reasoning of this is here. How we're reducing the space and why, like reasonably why we're reducing the space. So our formula here is just n factorial over n minus k factorial multiplied by k factorial. And with that, I'm just going to have you code combinations really quick. And there's a couple ways that you could do this, of course. You could base this off of, you could call out to permutations and make it a dependent function on permutations. You could, try to write it in a slightly more optimal way. That's fine. Or you could just code it directly. Any one of those options is absolutely fine. Okay, so let's go ahead. I'll give you 3 minutes to do this. Formula's right there. Write the function however you see fit, but of course you can just write it in its basic implementation as you see it here. Okay, go for it. Okay, so I'll write this in a couple ways. So we can just say def, get that, def combinations, and we can say n, it's n choose k. We can return the factorial of n divided by the factorial of n minus k multiplied by the factorial of k. That is perfectly fine. There's no reason to write something more optimal than this, but I'm going to anyway, just to give you a... We'll take that same idea from the slightly more optimal permutations function, and we can write that. Actually, I'll do this first, though. We can do combinations and return the permutations of n choose k and divide that by factorial of k if we wanted to make a dependent function. This is no more optimal than the prior function, though. Well, I guess it depends on which version of permutations it's calling out to. But let me write a third form of this, which is going to be, that sort of factorial form. And I'll say for I in range, n to n minus k, going down, right? We're going to do that, and then we can return the permutations divided by factorial of k. And one thing I do want to do on all of these is cast them to int. It's not it's not completely necessary that you do that, but remember, we're counting and we're going to assume whole numbers. So let's try to answer that question. Let's try to answer that question. Combinations, how many 5-card combinations can you have from a 52-card deck? We'll set 52 and 5, and we'll just see what that comes out to. Oh. What's going on there? Oh, I know exactly what's going on there. Okay. I'm still calling heaps up here. And there's the input in there. Okay. Okay. That is a lot of different combinations. And I think that's an interesting thing about this topic is, the topic of probability in general, but even just looking at permutations and combinations, the sheer size of some of this stuff, right? You've got a 52 card deck, 52 cards in a deck. How many 5-card combinations can you have from that? 2.6 million. That's wild. That's hard to grasp from just a human. We don't deal well with those numbers. We don't really understand those numbers in a more fundamental way. We're not like, oh, okay, well, it's hard to even grasp the likelihood of getting a subset of those combinations that will satisfy a certain goal, right? But you can start thinking about it probabilistically, right? I don't really know poker, but let's say a flush is a thing, right? I guess. What is the you could answer the question, what is the probability of getting a flush, right? You can start looking at that, and you can start weighing different strategies through the lens of probability with some hard numbers, and you can play a more optimal game based on probability as opposed to, your intuition, which in this space, we're constantly trying to, I don't want to say undermine intuition, but we definitely want to qualify our intuitions. And intuition has a hard time with 2.6 million. Intuition is in denial of that kind of number. And I think it's good to be aware of that. Okay. So from here, let's look at let's build some intuition around combinations. In the same way that we did with permutations, I have a similar approach that we can take for combinations. And so we'll build intuition around it, and then I'll code through a more optimal version and introduce something that you probably haven't seen yet in Python that I think is good to see, good to get a peek at early, and it's something that you'll use later on. So this is going to be very similar to what we did with permutations. So we're gonna count. We're gonna do our raw counts, right? Using whatever base system that we have, and we're going to create permutations. So we're going to reduce to permutations. And then we can sort these numbers, sort the permutations themselves, right? So sort elements in the permutations. And then from that we can reduce. So we can reduce to combinations by simply removing duplicate permutations. And as a kind of story problem for this, let's use basketball teams. I think is a good one. So, all right, I'm going to call this an expensive counting approach. That algorithm I just showed you is a little expensive, and that's okay. It's just a little expensive, and that's fine. Let's think about basketball teams. There's 5 people on the court. Doesn't matter. We're going to assume that it doesn't matter what position they're in. We just have 5 players, right? And if we have a normal squad of, I think it's 21, if we have 21 players, we would think that there is a number of combinations, 21 choose 5, right? That would be our number of combinations. So I'm actually going to assume that we don't have 21, but we have 11. I'm doing that because, interest of time, because this is going to take a little while to run. And 21 choose 5. Through this approach, if we're generating all the combinations, 21 choose 5 is going to have quite a bit more overhead than 11 choose 5. So I'm going to call this basketball combinations. And I'm going to set up this 11 numbers, and it's just going to be the range. We're going to assume that these are the numbers actually on people's jerseys, and let's just say it's 1 to 11. So we have player 1, player 2, player 3, up to player 11. And we're going to build every arrangement of 5, starting off by counting, right? We're going to do the raw counts. So here's a possible 5. The way that we're going to do that for I in 11 nums, right? This is just that basic counting. Here we're using a base 11 system. So 1, 2, 3, 4, 5. And I just need to change this to I, J, K, L, and M. Okay, and so with the possible 5, we can append each of these. So I, J, K, L, we could print those out, take a look at them. I think we trust that they're all there. So the next thing we're going to do is reduce to our permutations. How do we do that? We're going to remove any of these lists that we generated where we have duplicates. So last time when I did this using counting, using the count method. I'm going to do it a different way just to, bring back the list set trick. I'm going to say for each 5 in our possible 5, if the length of the list of the set of 5, that equals 5. Now, let me explain this. We're going to append that 5. What am I doing here? Notice that this is 5 long, right? If there are duplicates in here, like if j is 2 and l is 2, if we cast that to a set, then suddenly that thing is going to only have 4 items, right? We're going to be throwing away an item because we can't have duplicates. I cast that back to a list. I don't actually need to cast it to a list here. I could leave that out, but I just want to have it say list set because I want to get in your head the list set trick. The length of this, if it's not 5, then there was a duplicate. So it's just a little trick to qualify that. And I think that leads to a little bit of elegant code. It's kind of nice. In that case, if we still have 5, then we have all our permutations. So I will print this out. So let's look at our permutations. Let's print those 5. And I'll just go ahead and run this. And here are all of our permutations. How many are there? I think there's a lot. There's a fair amount. Okay. So from here we can reduce out again to our combinations. Okay, so at this point we're going to be collecting our combinations. I'm going to say for each 5 in those permutations, I am going to sort those, okay? And what this is going to do is, if we have a permutation that has the same elements as some other permutation, now they're going to look exactly the same. And in that case, I can check to see if that sorted 5 is already in our combinations. If it's not, then I can append them to the combinations. Oops, sorted 5. And that's it. We can return the combinations at that point. So let me call this basketball comms, and I'm going to say for combination in basketball comms, let's print the combination. Okay, you notice that paused a little bit, right? There was a little bit of like, and then it went. Let's try this. Let's see how this does with 21 instead of 11. And instead of printing these out here, I'm actually going to print these out as we go. So I'm going to print them in this. So let's do it here. So this will only print when we discover another combination. And the thing is, okay, so now we're getting into the combinations. And we'll get there, okay? We'll get there. It's going to take a little bit of time to run. And I think this is... If you think about what we're doing, we already did build our permutations, okay? We built our 21 permute 5. And now we're like on the path of discovering our combinations from the reduced permutation space. And notice we, it's doing this in starts and stops. And it will get there. It'll get there eventually. So one nice thing, just like with permutations, there is an inherent pattern that's here, although it's not as easy to see, I would say, as the inherent pattern that we saw in permutations. So this is still working. It's going to continue working. While it's doing that, I'm going to consider a different approach. Okay, this is what I'm going to call an expensive sampling approach. Okay. So instead of counting, we can take a sampling approach, and I kind of alluded to this yesterday when we were looking at, the sampling for coin flips, right? If you recall, we counted and we also sampled. Sampling, is actually just observing different ways that this might happen. And there's something a little bit maybe not entirely intuitive here. A sampling approach can take a problem that is somewhat intractable, right? Like this problem. This is still running over here in the background. We can take a somewhat intractable problem and make it a little bit more accessible. Or we can just sample as much as we want within a certain amount of time and then be like, okay, well, forget it. We'll just leave it after that. So the way that I would approach this from a sampling point of view, and I'll just write a function for this. So let's call this basketball combinations sampling. And something to notice here also, I can vary the team size. By default, I'll set it 11. I'll set the number of players to 5. And in this case, I can just make a collector for combinations. And the player range, we're still going to consider, player range is going to get the range from 1 up into the team size plus 1, okay? And from here, we're going to have a while loop that is going to perform this as many times as is necessary. This is a good place for a while loop because we don't know how many times we'll have to sample before we get all of the unique combinations. I'm going to say while the length of the combinations is less than, and this is just, I don't want to say this is me cheating exactly, but we have a formula for combinations. We know how many combinations we need, right? So I'm going to just utilize that. I'm going to say while this combinations collector isn't as long as the number of combinations we expect, then we're going to keep doing this until we get as many get all the different combinations of players. So let's say team size, number of players, and we're going to start off just building a single player combination. Okay. All right, so how do we build that? Again, I'm going to use a while loop. Let's say while the player length of the player combination is less than the number of players, right, which we're assuming is 5, then we're going to sample a player number. And that's going to be a choice from the player range, which is 1 to 11 or 1 to 21, whatever we happen to be doing. Okay. And if that player num is not already in the player combination, then we will append it. Player combination.append, and we'll append the player num. And I just want to point out that this thing is still down here working. It's still going for it. Okay. All right. So once we get 5 player numbers in there, 5 by default, then we're going to have this player combination that we can then sort, okay? This is its canonical form for us. We're just going to sort it, and then we can check to see if it's in there. So if the player combination is not in the combinations, then we'll just print it. So we'll print this player combination, and we'll collect it into this combinations. So .append, let's append the player combination, and at that point we should be able to return the combinations. So I'm going to get this one started as well. And comms sampling. And what I need to do up here is not call that other function, and just have to play with this a little bit. So let me do that and make a new terminal. And I'll have to navigate really quick to where we are. So make this a little bit bigger. And let's run this over here. So Python perms combinations.py. Oh, that's only doing 11. Let's set that to 21. And let this go for it. All right, so it's a race, except this other one, the counting one, started way earlier, obviously. So, you know, we'll just find out which one of those ends up resolving sooner. My money's on the sampling approach. This one's over here just chugging along, trying to figure out what's next. Okay. So both of these are expensive approaches. All right. And I'm not going to say that this problem is an intractable problem by any means. It's something that we can get through these more brute force approaches. But it turns out that there is another way that we can do this. There is a combinations algorithm that is present in the itertools implementation of combinations. So what is itertools? Itertools is a library right here. You can import itertools, and there is I'll just search for it. There's a permutations function. There's a combinations function, and these will get you the permutations or combinations for some collection, for some list, or something like that. If we look at combinations, here is an implementation, or here is a description of the implementation. And I'm going to write a slightly adapted version of that. And, oh, hey, the sampling approach finished. Now, I think this is counterintuitive, okay? This sampling approach finished because there's something it's not doing, okay? There are things that it's not doing that this counting approach over here is obviously doing, right? It is just working, and it has to sift through a massive amount of stuff. The sampling approach, even though if you would have been paying attention, which I wasn't, but if you were looking, it started slowing down toward the end, but ultimately it finished. What we don't have here, obviously, these are in no particular order, but maybe that's fine, depending on the problem we're trying to solve. So just keep that in mind. This is exhaustive. This is an exhaustive list of the combinations. And we did this with a sampling approach, and it is way faster than what we're seeing over here with the, sort of deeper counting approach. Okay, let's look at a faster algorithm. I'm just going to call this combinations algorithm from itertools, which will pass in a list, and we're going to look at k of those items. That's fine. And this is going to be a more general form of the algorithm. I don't think we need to put it in the basketball terms necessarily, but it'll solve the same kind of problem. So the first thing I'm going to do, and I'm doing this for a reason, is I'm going to get a frozen version of the list. What do I mean by frozen? It's in a form that can be passed in and out of the function, and I'm going to do that for a certain reason, which I'll explain in just a second. So list frozen is going to get tuple of the list, right? Tuples are immutable, so that tuple, it's going to serve us well. And n is going to be the length of list frozen. That just makes sense. You know, we're thinking n choose k. That's just how many items we're dealing with. There's a little bit of fault control I'll do here, where if our k specified in the function header, if that's greater than n, then something's broken, right? K can't be greater than n. K has to be less than n. Less than or equal to n. Okay. So remember last time I did something where with permutations, I had some form of memory. And I'm going to have a similar thing here. In this case, I'm calling it our indices. And this is going to be our memory for these operations. So it's just the range of k. So if it's 10 choose 6, right, this is going to be 0, 1, 2, 3, 4, 5. Indices, 0, 1, 2, 3, 4, 5. All right, so I'm going to yield here. Yield is why I'm freezing things, all right? If something is a tuple, or if something's immutable, we can pass it out of the function. And what this is going to allow us to do is take something at a moment in the function and just put it in a state that it can be returned from the function. Okay, so it will be it's going to be a thing. It's like returning, but it's sort of like returning wherever without ending the function. Okay, yield is very powerful. You can use it to make things called generators that are way less computationally expensive, and they're more Pythonic. They're a more Pythonic paradigm when you get to them. So this is a very, very light introduction to yield. At the end of the day, we're going to get a function that returns something for us, which is really what we're going for. But I'm going to yield the tuple list frozen sub I for I in indices. So if you think about what that's doing, this is going to be 0, 1, 2, 3, 4, 5, 6 if k is 6, right? So this would just be the first 6 items if k is 6, or the first 2 items if k is 2, right? And we're just getting that one out first. So we're just getting that first combination. And then I'm going to do this thing called while true. You know, one of the scariest things in programming is the while true. But it's okay. We'll break out of it. We're going to have some sort of fault in here that allows it to break. And then I'm going to reverse the range of k. And if indices sub I is not equal to I. So think about this. The reversed range of k, if k is 6, is going to start at 5. Okay, I is going to be 5. And it's sort of like as long as indices sub I is not equal to I plus n minus k, then if that is not the case, we're going to break out of this for loop. And then we do have a return. This is our end when we get down to it. So we're expecting this for loop to run until we've exhausted our possibilities. And I'm incrementing kind of our pointers as we go for indices sub I. Notice I is going to be changing as we go. And I'm going to say for j in range, I plus 1 up to k, indices sub j is going to get indices sub j minus 1. So the state that is in our indices. And we're going to be able to yield. Notice I have to cast it. I have to make this a tuple in order to yield. List frozen sub I for I in indices. Okay. All right. So these are all rearrangements happening. And, sorry, not rearrangements. These are all sub-selections that are happening. And one really nice thing about this is we're not going to be skipping much in the way of operations. So let's just try this out. And let's do this with our list will be the list of range from 1 to 21 plus 1. And let's consider this. So this is the same basketball team problem. 21-person squad, 5 people per potential team. And let's see. Oh, you know what? Let me traverse this. Let me say for team in that, let's print that team. Okay. Just so it's kind of in the same format as before. Oh, list frozen is not defined because it is LST frozen. That's why. Okay, let's try it again. That was pretty quick, right? That did not take very long at all. So that is a much more optimal approach. The sampling approach wasn't bad, but kind of the lesson here is that there's a better algorithm. There is generally going to be a better algorithm, and a lot of these problems are solved. Just to be clear, but it's good to, how do I say this? It's good to look at different simple ways, right? This expensive counting approach, for example. I think it's good to look at this and understand what's happening there. It's good to look at this sampling approach, and then once you have these simpler algorithms, like locked down, understandable, then you can work on understanding a more complex algorithm. Although, with these, with the iter-tools combinations and heaps for permutations, don't worry about understanding those unless you have the bandwidth before the technical interview, right? The deadline for the TI, I believe, is I think for people in this course, it's the 16th. Is that right? Monday the 16th? I'm just double checking to make sure. So, you want to focus on the places where you really need to put focus, which probably isn't going to be these more advanced algorithms, but you do want to be able to, you do want to understand, let's say, this basketball combination sampling, for instance, and also this reductive approach for combinations and the reductive approach for permutations as well. This is a lot of code. I'm not going to paste it in. What I'll do instead is just link this, like we usually do, link the video and then link the code. Okay, let's take a 6-minute break. That's it. That's going to be it for permutations and combinations. We're going to move into there's a concept that we teach describe as the general analytic approach. We've already been doing it, but we're going to go into that, kind of formalize it, in the remaining time for today. So I'll set 6 minutes, and I will see you all back here shortly. Oh, I'm sorry, my mic was off. So we're going to switch gears a little bit, and we're going to get into something that I refer to as a general analytic approach. And what I mean by this is we kind of boiled out what we want you to be able to do on the technical interview, okay? And what we boiled out is not just relevant for the technical interview. It's kind of a more abstract approach to investigating a problem. And we're going to do this from a couple different perspectives, okay? So let me just open that up. Okay. So for us, we have this idea of a general analytic approach. And it's really just about trying to solve a probabilistic problem that you don't know how to solve yet, is kind of what we're getting at here. And, there are three categories of this that we'll consider. We're going to consider a counting approach. We've already been doing a lot of counting. We're going to consider a sampling approach, which we've already done a fair amount of. And what we haven't really done, we've totally done this. We're going to take a closed formula approach. Although what we've done with the closed formula approach with permutations and combinations is we've just answered very direct questions, right? Like, how many permutations are there of 12 permute 4 or something like that would be an example. So what is this analytic approach? We're going to think about it in just generally 3 steps. One, we're going to kind of synthesize outcomes, right? Which we can also think of as modeling a phenomenon, or even just looking at data, right? Maybe we have some data and we're looking at it. Any of those things. Then we're going to interpret. We're going to observe, right, and interpret, right? This might be some descriptions. Maybe we look at the mean. Maybe it could be any number of things. We're just going to look at the thing that we made, look at the synthesis, or look at the data itself. And then we're going to answer questions. And this is, kind of generic purposefully. We want you to be able to think in these terms, by looking at, say, a distribution, or looking at, a known distribution, let's say, or maybe rolling a die and pulling a card from a deck of cards and, some other probabilistic thing, and, processing that through some other equation and looking at the result and then describing that distribution, right? This can be for things that are known or unknown, and we want to keep it very general for that reason. So let's talk about counting. We've been doing this, and one thing that you might notice about counting is that it is exhaustive. If we have, binary, some sort of binary system where, 0 is, let's say, tails, and 1 is heads, for 3 subsequent coin flips, we can exhaustively represent this by counting, right? This is, there are 8 different potential outcomes for 3 coin flips of a fair coin, and this is them. This is all of them. And we can answer a question such as, what is the probability of 2 heads? Well, exactly 2 heads, not 2 or more. 2 heads, well, that's this, and this, and this, right? Is that it? So that's 3 out of 8. No, there's got to be one more. No, that's it. I'm sorry. Yeah. We can answer that, and notice that because this is exhaustive, this probability is exact. Okay? We can do this mostly for, we're mostly going to think about this for discrete kind of data, discrete systems. But we could also do this for, something that is more continuous if we make bins. Although in that sense, we may not be as exact. So let's think of an example here. I've got something here. So in a particular tabletop game, when in battle, a player first rolls a 36-sided die, then pulls a card from a standard deck of cards, and finally the player flips a coin 3 times. Okay, so step 1 of this is going to be to synthesize some outcomes. How do we do that? Okay, so a player first rolls a 36-sided die. So I can just do this. This is going to be the range from 1 to 36 inclusive. That's the rolls of our 36-sided die. Now, the next thing they do is they pull a card from a standard deck of cards. Okay, this might take a little more to set up, but we can do this in a somewhat, in a pretty systematic way. Spades, clubs, diamonds, and hearts. And then our card numbers are going to be 2, 3, 4, 5, 6. Oh, you know what? I should probably make these text. 2, 3, even though this is going to take a lot longer to write. 4, 5, 6, 7, 8, 9, 10, and ace. Okay. And if we want to construct this deck of cards, we can say for suit in suits, for card in our card numbers, we can just say cards.append, and I'm going to append this as a string. I'll say card of suit. So that's pretty straightforward. If we want to just show that this is working, in fact, we can do that. And we have a deck of cards, right? 4 of clubs, 5 of clubs, 6 of clubs, 7 of clubs, 10 of clubs, ace of clubs. Oh, you know what? We don't have all of them in there. Sorry, ace, jack, queen, and king. There we go. That should get us everything. And it does. Okay. So that is going to get us our cards, and then the last thing, finally, the player flips a coin 3 times. Well, we know how to do that. So let's say coin flips. Again, we're just going to count these. I'm going to say for flip 1 in tails and heads, and then we'll just do F2 and F3. And we can say coin flips dot append will append a list of F1, F2, F3. Okay. All right. So if we want to create our sample space here, we can put all of these components together. And I'll just call this capital S for the sample space. And we're going to say for each roll in rolls, for each card in cards, for each flip in our coin flips, s.append, and we'll append the roll, the card, and the flip. S is going to contain every possibility that we have here. How many different outcomes are there? Let's print the length of S. We can just see. I think there's going to be a lot. 14,976. And that is us synthesizing our outcomes. We can imagine that suits and values matter in this game. I think with the questions I have around this, I don't make them explicitly matter, but we can imagine that they do, and in a number of different ways. Like maybe in battle, your opponent is sensitive to a certain suit, right? That could be the case, right? Let's look at step 2 of this. I think, we could say step 2 is just observing, interpreting this. So for each outcome in S, maybe we just print our outcome. And let's just take a look at what this looks like. 36, King of Hearts, heads, heads, heads is the highest thing. Of course, there's like 14,000 of these. If we scroll up, 31, Jack of Diamonds, tails, heads, tails. There's a lot here to work with. There's a lot of randomness that we can play around with. And this brings us to, kind of step 3 of this general analytic approach, which is answering questions. And let me actually throw this also in the Slack before I comment it out. So you're going to utilize that code that I just gave you to build. So I built the sample space for you and gave you, sort of a look into it, and you're going to answer a couple questions. Let's look at this breakout. So suppose that the 36-sided die represents the range of an attack. To hit an opponent, that opponent must be in range. So let's say you roll 29 on this 36-sided die, then you can potentially hit the other player if they are 29 or less spaces away. Let's imagine this is a like a hex, a hex board where there's kind of a single best path. The card represents the amount of damage that the attack will commit. In order to actually inflict damage, 2 of the 3 coin flips must be heads. So what is the probability of hitting an opponent that is 18 spaces away? That's the challenge. I'm going to give you 6 minutes to do this. And share the code snippet and also share the probability that you arrive at. Okay, so let's solve this. So we've got S, and let's okay, so let's find all the instances that are potential hits. Okay, so I'm going to call this hits, and from that, well, we need the conditions that we're using to filter. So I'll say range to hit, and so we need to roll an 18 or greater. And I can say for each outcome in S, if outcome sub 0, y outcome sub 0, well, it turns out that outcome sub 0 is our roll, right? That's our roll. So if the outcome sub 0 is greater than or equal to the range to hit, then there's a potential that that is going to work. And then I'm going to do this as a nested if. You could do it as a compound condition. If outcome sub 2, dot count of heads is equal to 2. Okay? In order to actually inflict damage, 2 of the 3 coin flips must be heads. Exactly 2 of the 3. If that's the case, then we can say hits.append will append the outcome. And I'll just go ahead and print the length of the hits divided by the length of S. And I think in this case, it's a good idea to round this. And I'm going to round it to 3 places. So, oops. So let's see what that is. Looks like it's 0.198. So there's a fair chance of hitting, making a hit in this case. And if we want to think about that relationship, right? Well, what is 18 divided by 36? First off, it's 0.5, right? And then what is the if you think about how we're modifying this, 0.5, and then we're going to modify it by the number of occurrences where there are exactly 2 heads. Maybe I'll even modify this further. So 2 heads gets, well, let's do that. And we'll just also collect this. So I'll take this. I'll say 2 heads, dot append, that outcome. And let's print 2 heads divided by the length of S, and we'll round that. Again, 3 places. Oh. Probably because I need to get the length of 2 heads. So it looks like that's 0.375. And let's say, let's do this. So, maybe I'll just do something like this. Why am I getting that error? Oh, because I'm rounding to 1. And I want to round to 3 places. So multiplying these two together gets us very close. We get 0.188 in this case, but I think that's because we want, let's see. This might actually need to be 19 out of 36 if I'm thinking about it correctly. Yeah, yep. So it turns out that we can, there are a couple different ways that we could solve this, right? We could figure out each of these sets of outcomes independently and multiply them together. 19 out of 36 because there's actually 19 ways that we could hit if they're 18 away. I just made a slight mistake. Or we could filter, we could do this sort of like compound conditional statement in order to filter. So that's kind of, I think that's a reasonable demonstration of our analytic approach. And it's a bit of a here's kind of a, I don't want to say a throwaway problem, but it's, we're talking about decks of cards and rolling dice and things like that. Well, we're going to get into some distributions that you do need to know pretty soon. And those distributions show up in a lot of places. We focus in on them because, they're good for gauging your quantitative literacy. They're good for, they're good because they show up in a lot of other equations and other problems, and we can make real-world examples of them pretty easily. Okay, so let's see. Do we have enough time? Let's just try to get into a random sampling example, and we might not go all the way with this one today. We might pick this up in our next lecture. Okay, so we're going to take a random sampling approach. We just took a counting approach. Now we're going to take a random sampling approach. So let's consider invitations sent for a party. It says as if, because I think I wrote this at the beginning of the pandemic. 20 invitations are sent out. Each guest can possibly bring up to 10 guests, with equal probability of between not going and 10 guests, where 10 guests would be that person going and brings 10 more people. No matter what, at least one person, you, will be at the party. So how do we start modeling this? How do we model this situation? We'll probably have to make a couple choices about, how to interpret this. But, we can start thinking about it most easily through randomly selecting numbers of guests, essentially. So let's say I'm going to write a function called number of attendees, and no matter what, there's going to be at least one, right? The host. And then I'm going to say for whatever in range 20, right? Because there are 20 invitations that I, as the host, am sending out. The number of people is going to be incremented for each of those 20 people by anywhere from 0 up to 11 people, right? Because it's the person plus 10 potential guests. So this should model that phenomenon. And this is, let's see. We'll essentially leave it here, but I want you to think about what your intuition says. Looking at this. How many people do you think this will end up being, right? You're inviting 20 people, and those people will either come or they won't, or they'll bring, up to 10 guests if they come. And we made a choice here, okay? And I don't want, not just the choice function, but we made a choice in that we're deciding that there's equal probability that they will bring themselves, bring one guest, bring two guests, bring three guests, bring four guests, brings five guests, right? So we're making a determination there. We're not deciding first 50-50 chance that they're going to come or not, and if they do come, they're going to bring, anywhere from 0 to 10 guests. That would actually be a different problem, right? That would be a different problem. So we have to make a choice here in how we're modeling the phenomenon, and this is the choice that I'm making. Although we could write this in a different way, and we would see a different outcome. Take a guess. Just throw a number in the Slack about, roughly how many people do you think are going to come to this party? And just use your intuition. Think about it for just a second and just throw some numbers in there. How many people you might expect. $111, $100. Yeah, these are some good guesses, and I think this is sort of contingent on your intuition, right? A little bit, but also if you look at the problem, 20 invitations sent out, and you're going to get roughly how many people from each invitation if there's an equal probability between 0 and 11 people, right? Think about it. Like 5.5, probably. On average, that's what you're going to get. So 5.5 times 20 plus 1 is a good guess at an expectation. Okay? And let's just run this a couple times and see. So I'm going to print the number of attendees. 108, 111, 123, 115, 106, 103, 114, 125. If we want to get a better picture of the sort of the possibilities, we can do that, and we'll do that next time. We'll pack this into a dictionary. With our materials, we focus quite a bit on dictionaries, and with these general analytic approaches, often we're going to be building dictionaries. So we'll start getting into those in the next class, and we'll pick up on this slide deck when we get there. Cool.